water, the most common, the most vital, the most extraordinary liquid in the world. Extraordinary that it is a liquid at all. Extraordinary because when solid, it is lighter than the liquid from which it forms. Extraordinary because when heated, it evaporates much more slowly than other liquids of a similar molecular size, carbon tetrachloride or petrol, for instance. Its surface tension is so high that metals can be made to float. It will dissolve almost anything. It is highly corrosive, rusting away steel. Yet it is harmless to living things. Indeed, it is vital to life. What is water? Why is it unique? What is a molecule of water like? Water can be produced in the laboratory from its simple elements: oxygen and hydrogen. When hydrogen burns in oxygen, two atoms of hydrogen combine with one of oxygen to form water. But this basic formula gives no clue to the nature of the water molecule. How do hydrogen and oxygen atoms combine to form water? An atom is often pictured as a solid sphere. It is, in fact, remarkably empty. In the center is a nucleus, heavy and compact and very small. Orbiting the nucleus at great speed are electrons, negatively charged. For the moment, let's think of them as particles. The nucleus consists of protons, which are positively charged, and neutrons carrying no charge at all. The atom itself is electrically neutral because the positive charge of the protons balances the negative charge of the electrons. Electrons can be imagined as orbiting in a series of layers called shells. But there is a limit to the number of electrons in each shell. The first shell can hold 2 and must be complete before a second shell is formed. The second shell can hold 8 electrons and in turn must be filled before the next shell is formed. The heavier the atom, the bigger the nucleus, the more shells are needed to hold the electrons. For water, only the first 2 shells need be considered. First, hydrogen. The first shell can hold 2 electrons, but the atom of hydrogen has only 1, leaving 1 vacancy. Now for oxygen. The first shell is full. The second shell contains 6 electrons, but it could hold 8, so there are 2 vacancies. When there are vacancies, an atom tends to fill them to become more stable. One way to fill these vacancies is by sharing electrons with other atoms to form a molecule. When 1 oxygen and 2 hydrogen atoms share electrons, water is formed. A two-dimensional representation goes some way to explain the molecular structure of water. But now think of the atomic system as three-dimensional. Think of the electron as forming a cloud, an electrically charged cloud around the nucleus. The cloud corresponding to the first shell is spherical. Hydrogen has one electron in this sphere. Oxygen has two. It is therefore complete, and a second shell must be formed. The second shell electrons make up four separate clouds. The first, again a sphere, holds two electrons. The other three clouds are dumbbell-shaped and set at right angles to one another. Each can hold two electrons. Three electrons enter separate dumbbells. The last electron pairs up to fill one dumbbell cloud. This leaves two dumbbell clouds still incomplete, and therefore available for bonding with two hydrogen atoms. Before these atoms can combine to form water, energy is needed. Very much simplified, what happens is this. The energy causes the oxygen atom to become agitated and unstable. In the second shell, the sphere and the three dumbbells hybridize and distort into four pear-shaped clouds. Two of these clouds still have their vacancies and are available for bonding. The hydrogens approach. A bond is formed, and a molecule of water is produced, H2O. It is the electrical forces in the new molecule which result in its non-linear shape. Because the oxygen nucleus contains 8 protons, and the hydrogen nuclei each contain only 1 proton, the negative electron clouds are pulled towards the greater positive charge of the oxygen nucleus. As a result, the hydrogen ends of the molecule are left with a positive charge, while the oxygen end develops a negative charge. It is this arrangement of electrical charges which gives the water molecule its unique directional characteristics and determines the way it behaves in a mass. This can be seen more easily if the form is simplified. Each water molecule attracts neighboring molecules, because the two negative ends of one molecule attract the positive ends from each of two others. They attach like hooks and eyes to form hydrogen bonds. Here is the basis of the unique properties of water, enabling an extended and open structure to be built in 3 dimensions. However, although at normal temperature hydrogen bonds are forming spontaneously all the time, heat motion keeps breaking them. The situation is never static. If all the hydrogen bonds joined together, water would be a solid. If they all broke, it would be a gas. Water is a liquid because they are forming and breaking continuously. This, then, is water. So the extraordinary behavior of water can be explained by the nature of the electrical forces in the molecule and the resulting hydrogen bonds. Hydrogen bonding explains why water is lighter solid than liquid. Like all other liquids, water contracts as it cools. The molecules pack closer together as heat motion is lost. At 4 degrees centigrade, water reaches its densest point. Then, as it continues to get colder, a change becomes apparent. Unlike other liquids, which can go on contracting, the molecules of water begin to form an open structure because increased hydrogen bonding reduces the tendency to close packing. Until at zero, providing crystal-forming nuclei are present, ice starts to form in a rigid, empty structure, lighter than the water itself. So, ice floats. Condense hours into seconds and see ice form. If ice were heavier, seas and lakes would freeze solid, and life in the sea as we know it would be impossible. But above, clouds far colder than ever is the sea will not form ice crystals unless there are solid particles present, mineral salts or crystals of preformed ice to act as seeds. As ice forms, the molecules take up their completely ordered hexagonal pattern. Rigid networks form, as hydrogen bonds hold every molecule in a fixed position. Ice, then, has a definite shape and volume. As ice melts, the bonds start to break. The networks become fewer, smaller, and shorter-lived. In the liquid state, small networks still exist, but everything is moving and changing. The networks breaking up in some places and reforming in others. At any given temperature, water has a definite volume, but unlike ice, no definite shape. As water is heated, the life of each hydrogen bond is reduced. The molecules vibrate more and more, straining and breaking more of the hydrogen bonds which hold them together. Extra heat energy is needed to raise the temperature of water because some of the energy is used in breaking the hydrogen bonds. Even at boiling point, a great deal of heat is needed before the remaining hydrogen bonds finally break, to result in the third state of water, gas, with neither fixed volume nor shape. The fact that heat is used up in breaking hydrogen bonds explains why water needs more heat to evaporate than other liquids of a similar molecular size. The strength of the hydrogen bonds also explains surface tension. In the body of the liquid, the hydrogen bonds between the molecules pull equally in all directions. But on the surface, the pull can only be sideways and inwards. So water finds the smallest possible surface area for a given volume. A sphere, or as close to a sphere as the force of gravity will allow. Injected into a liquid of equal density, it adopts its perfect shape. Surface tension shows in the shape of the meniscus, held almost as though by a skin. More water enlarges the meniscus. But adding a surface active agent, such as a detergent, reduces the surface tension. The strength of this skin on the surface of the water comes from the hydrogen bonds. The unique power of water as a solvent can also be explained by the hydrogen bonds and the electrical properties of the water molecules. When water dissolves sugar, hydrogen bonds form between the molecules of water and sugar and hold them in solution. But when water dissolves salt, seen here under the microscope, it is taken into solution in a different way. The electrical attraction of the water molecules for the sodium and chloride ions is greater than the attraction holding the ions together. The positive ends of the water molecule pull on the negative ions in the salt, and the negative ends pull on the positive ions. The crystal structure disintegrates as the bonding forces between the ions are destroyed and the ions go into solution. Water comes very close to being a universal solvent, and because of this, it is the medium through which most chemical reactions in living things take place. When oxygen and hydrogen combine, a molecule of water is formed. The electrical properties of the water molecule determine its behavior, particularly its directional character. Having negative and positive ends makes water the almost universal solvent. The negative and positive ends form hydrogen bonds which hold the molecules together. It is the hydrogen bonds which produce water's high surface tension. At normal temperatures, the hydrogen bonds are forming and breaking all the time, keeping water a liquid. When hydrogen bonding is complete, ice is formed, open in structure and lighter than the water from which it came. When all hydrogen bonds are broken, water becomes a gas. The heat energy used up in breaking the hydrogen bonds explains why water needs more heat to evaporate than other liquids of a similar molecular size. It is the ability of water to absorb heat that prevents excessive changes of temperature on the surface of the Earth and provides the stable environment necessary for life. This, then, is water, the most common, the most extraordinary liquid in the world.